Hey guys, so today we are learning about global navigation satellite systems. First of all, we'll take a look at all the radio locating methods. So radio locating method is a process of finding the location of something through the use of radio waves. And we'll look at first what is GNSS. So some famous GNSS are GLONASS, that's a Russian uh, global navigation satellite system. Then there is GPS that you all know, Global Positioning System from USA. And then there is Galileo. That's from Europe and it has been there since 2016. So the method that the satellite communication take in order to locate a certain place, they use the time period readings. So as you all know the mathematical formula that distance is equal to velocity multiplied by time. And in the case of satellite navigation, the velocity is the speed of light because radio waves propagate at the speed of light. And there is another big difference between GLONASS, GPS, and Galileo. That is that Galileo doesn't have a military background. GLONASS and GPS were first made by military and then they were further used for civil purposes. So moving over to functioning of a GNSS. So satellites are orbiting around the Earth and at a specific time they are at a specific point in space. So there is an uplink station that is attached to the space segment of a satellite system. Uplink station refers to all the communication that is being held between the station and the space segment. So there is also a downlink station, as in at the downlink station, the all the data that is being received from the satellite, it is known as downlink. So there is also a TT and CC, that is telemetry, command, tracking and control the station that controls the movement of all the satellites and their telemetry positions and tracking and all. So moving further, every single satellite and they have an atomic clock, and there is a very big reason of why they use an atomic clock, because they all have to be uh, precise. If we take an example, if the receiver on Earth wants to know his location, but at the same time when the satellites try to track this specific receiver on Earth, and if there is a time difference of 0.1 seconds from the clock of the receiver and the clock of the satellite, then this would result in a location difference of around 30,000 kilometers. So that's why they need to be precise. That's why they use atomic clocks from rubidium and cesium. So they send non-identical signals at the exact same time. The receiver on Earth receives the signals and can identify which signals belong to which satellite. So the receiver has no atomic clock. We got a time difference error. Even if it's 0.1 second, it will result in like 30,000 kilometers away. Satellite time would be sent with the radio signal to the receiver at the time of locating the receiver. So for a three-dimensional position calculation, we need three satellites at least, so that we could determine a 3D location. But then we use another satellite in an orbit of a global navigation satellite system. We have a minimum of 4 satellites rotating in the same orbit. That is because the fourth satellite can be used to determine the time difference between the receiver. So here you can see 4 mathematical equations, and you can take a look at xi, so as in x1, x2, x3, x4 are the x coordinates of all the satellites from 1 to 4. So x, y, and z, x1, y1, and z1 determine the position of the first satellite, and x2, y2, z2 determine the position of the second satellite, and so on. x4, y4, and z4 determine the position of the third and fourth satellite outside in space segment. And then there is ux, uy, and uz. That is the unknown user location on Earth. So on the other side of this equation, you can see R and C. So R is the time period required by R1 is the time period required by the satellite 1 to send the data to the receiver. So the time period that is taken by the signal to transfer from the satellite to the receiver is considered as R1, and CB is considered as the receiver clock error. So we have four equations here, and through these four equations we can determine the precise coordinates of the receiver. So the moving over to the error sources for a GNSS. So they multiple path reception in valleys and inner cities can cause error while using global navigation satellite systems. Attenuation and shadowing of a signal, as you can see in the picture, also occurs, and that can also lead to problems while locating through GNSS. Low satellite visibilities and viewable satellites, aligned plane sliding sections. So a GNSS can have up to 30 satellites in total. There is this TT and CC station that controls and coordinates with the satellites. The receiver must have a visible contact with the satellite, and around one measurement per second is possible. And the normal exactly determined location from the satellite is around 10 meters. So there can be up to 10 meters of difference, but it's not that big. And it is not easy to check the integrity of a signal while we're talking about global navigation satellite systems. And here on this page you can see say a space segment of a GPS, a type of GNSS. So you can go through these in free time and read the possible things that are used in a GNSS.